as well as, even though we're only going back about maybe 1% back in through geologic time, even at 1%, there's been tectonic and oceanographic changes. So we'll talk about that as well. And so first of all, let's just introduce what I do. I'm a paleoclimatologist and a paleoceanographer. So climatologist and oceanographer, we decipher climate and oceanographic changes, sometimes from thousands, but most of the time, most of my records are millions to tens of millions of years ago. And this is me on East Antarctica. And this is the big drill ship called the Georges Resolution. It's part of the International Ocean Discovery Program. That's where many of the climate records have been taken. So let me show you a little bit about some of the places I go to, and so where I get my data and sediments from. All these circles represent where I got samples from. The stars represent where I actually went on expeditions. And so actually I did my PhD, my graduate work at Rutgers University, and we actually worked on cores along the New Jersey coastal plain, going back all the way back to the time of the dinosaurs, back to the late Cretaceous. But I've been on 4 expeditions to Antarctica, and one of them was a drilling project on the continent, actually on the sea ice, just off the continent. You can actually see an extinct volcano in East Antarctica right here, where we were able to get cores going back to about 20 million years, and we were able to get sediments and penetrate below the seafloor up to about almost 4,000 feet. Okay. I was on an oceanographic expedition where we were getting sediment cores just off the coast of Antarctica. We got sediment cores as old as around 51 million years old. And one of the scientists discovered pollen that comes from palm trees from that oldest core that suggests that indeed that Antarctica was much warmer than today. And one of your questions would be, well, maybe Antarctica tectonically was further closer to the equator. No, it was right over the pole at that point. So what happened? Okay, and the answer is higher greenhouse gases. Another expedition I actually led where we were sleeping on the sea ice in these tents, 2 people to a tent, brought down 4 students with me. They all have their toes and their fingers, so that was pretty good, and they got lots of extra credit. And in this case, we used seismic, basically sound waves, to image the sediments below the seafloor. So they were basically, the analogy would be sonograms of Mother Earth. Okay, and we were able to see the different layers going back down to over about 2 kilometers, so a little bit more than a mile down. We were able to image these sediments. And then the most recent expedition I was on was in 2017, and this was with the International Ocean Discovery Program. And this is the one where we explored the newly named 8th continent of the world. And this is the last continent we're going to find on Earth. The next continent will be on another planet. Okay. But before I go on, let me just acknowledge, climate change, I make a big deal about it, and it is the major crisis that's going to face humanity for the long term. But I just want to recognize that the pandemic and the resulting recession is causing a great deal of pain in and around the world. But the coming disaster from climate change is going to be far worse. And so what my research is to look at past examples of when CO2 was higher than today and see if we can say something about what's happening today, what's going to happen for our future. And so I'm just going to have this a few slides because I know that everyone's on board here. There's no climate deniers in this group, hopefully. And so the y-axis on the left side here is degrees above the 20th century. On the right side y-axis is carbon dioxide parts per million. And you can see in the red, which is carbon dioxide, and the black, which is global temperatures, the global temperatures have been rising. They've been steadily rising faster and faster since about the 1960s and 70s. And so there's a good correlation with that. And I just want to mention, I'm not going to go spend 20 slides on this, but there are scores to hundreds to maybe thousands of scientists working on each one of these topics. Ocean temperature shows evidence of anthropogenic warming, sea ice extent, northern hemisphere snow cover, so on and so forth, sea level rise, sea surface temperatures, all of these have hundreds to thousands of scientists working on this, and we see the same, and they're coming up with the same conclusion, that the climate is warming and changing, and it's due to humanity. It's due to us. So, and that's all I'm going to really say about that. Okay, so, but why should we study past climate changes and collect data? Okay, and that's because the future is data poor. Now, we do have climate models that are getting much more accurate than say 10 or 20 years ago, but still, we have examples of the past. And so we know that the climate is changing. It's going to be impacting us and the entire world. And it's by understanding the history of long-term climate change can we hope to understand current climate patterns and better predict future climate changes. And that's what I do. That's what I do. And so, in fact, the last time that the atmosphere changed more quickly than what humanity is doing right now was about 65 million years ago. Okay, 65 million years ago. And what happened back then? An asteroid hit the Earth and wiped out the dinosaurs and about 76% of all the other species. Okay, well, and let me tell you something. It wasn't the dinosaurs' fault the asteroid hit the Earth, and they couldn't do anything about it. In our case, in case of humanity, we are causing a problem, but we can correct it, and we have the solutions. And so, what do some of the climate records have? Okay, this is from ice cores, okay, where we have carbon dioxide, methane, temperature. I just want to work on, just look at the carbon dioxide. And you could see that with the carbon dioxide, and I mentioned, this record goes back, I almost forgot, goes from today back to 800,000 years ago. This is the longest ice core we have. It's the Pekar ice core from East Antarctica. And you can see that the CO2 levels just barely get about 300. We now know, okay, we all know that CO2 today is over 400, it's around 415 parts per million. And the last time it was that high was 3 million years ago. MA just means millions of years ago. So what we have done in a little over a century, Mother Nature couldn't do in millions of years. But so what about our future levels? Okay, 450, 500, these are thresholds of trying to stay below 1.5 degrees Celsius that the IPCC is talking about. 500 keeps, would be raising temperatures of global temperatures about 2 degrees Celsius. But if we continue with business as usual, we're shooting for values that are between 700 and 900 parts per million. We haven't seen anything like this in tens of millions of years. So what we're going to do in 2 centuries, Mother Nature couldn't do in tens of millions of years. I know we're on the same, I'm talking to the choir here, but it's good to know that the paleo records show that what we are doing is so unique, so precedented, so unusual, okay, what we're doing to the atmosphere and then the resulting climate change. And so we talked about CO2. Let's talk about global temperatures. And the last time it was about as warm as today, or 1 degree warmer than pre-industrial, because we're at this level now. We're at 1 degree warmer than pre-industrial. The last time that was about 6,000 years ago. And that wasn't because the people were running around in, in Mesopotamian SUVs. It was because the shape of Earth's orbit goes from a perfect circle, or near perfect circle, to a little bit more elliptical every 100,000 years. And the important word here is 1,000. So we're talking about 100,000 years. Also, the axis of the Earth changes. There's 2 different cycles. One is 20,000, the other one is 40,000. Again, the most important word I'm saying here is 1,000, not 100 or decades. Now, the last time it was a little warmer than today, or 2 degrees above pre-industrial, we haven't seen that in 125,000 years. And this is when humans lived in small communities. And again, it wasn't because of the cavemen driving around in SUVs, unless you think The Flintstones is a documentary, and it ain't. So, and with a 1 degree warmer than today, sea level rose by 20 to 30 feet above today. Okay, that doesn't mean it's going to rise like this in in a couple of decades. It'll still take centuries to rise 20, 30 feet, but we don't need a 30-foot sea level rise. 3 or 4 feet would be catastrophic. When it was significantly warmer than today, and when CO2 was about as high as today, was about 3 million years ago. And this was because CO2 was higher than pre-industrial. And sea level was about 40 feet higher than today. Now, again, this one, we're not gonna, don't go home and think that Dr. Pekar or Steve said sea level is gonna go up 40 feet in this century. It would take centuries to a millennium to cause this. But like I said, we don't need 40 feet, we need 3 or 4 feet. But the last time that CO2 is as high as what we predict for the end of the century occurs between about 25 to 50 million years ago. Actually, it's about 15, but let's call it 25 to 50 because that's significantly higher. And during that time, the Antarctic ice sheet was a dynamic ice sheet. It was expanding and collapsing with over 100 feet of sea level change. This is what the paleoclimatologists know. This is what we do for a living. We figured this out. Now, in terms of paleo CO2 records, most of this is from deep sea sediments. And you're probably thinking, how do you get a CO2 value from deep sea sediments? Well, that's for another story, but I'll show you in a slide or two a little bit about it. So the x-axis is on the right side is today, going back to about 66 million years ago, just at the time of the demise of the dinosaurs. And you could see that CO2 was just about at 400 parts per million about 3 million years ago. It was about a little higher, about 500, about 15, 16 million years ago. And then it gets way into the upper hundreds to near 1,000 parts per million once we get back 35 to 45, 50 million years ago. Okay? This is what we know as scientists. Okay, so some of the times I'll be talking about is the late Miocene. I'll actually talk about the Middle Miocene Climatic Optimum. The later Oligocene, which is a conundrum that there was some controversy, and I'll show you how one of my graduate students basically resolved that pretty nicely. And then during the super warm period between 40 and 50 million years ago, when CO2 was as high as 700 to over 1,000 parts per million, I'll talk a little bit about that as well. Okay, so here's some of the records that we get from the International Ocean Discovery Program. So we get the CO2 records that I just showed, oxygen isotopes. I'll talk about that a little bit at some point. That gives us a proxy for climate overall. And then we have a new, it's 20 years old now, magnesium calcium that just gives us water temperature. So it's a proxy for bottom water temperature. We have that. And then we have sea level reconstructions. And this is actually from my advisor, from my PhD advisor from Rutgers. And actually the part that I worked on was right in here. Okay. So these are some of the proxies. These are some of the records we are working on today. And so let's talk about ice owing, because that's what I'm going to be talking about for most of this talk. And so this is the Antarctic continent. If we removed all the ice, the blue represents below sea level. And you're going, whoa, whoa, whoa. Lots of Antarctica is below sea level, especially West Antarctica. And yes, and that's because the thickness of the ice has weight. The ice basically weighs down on the lithosphere, and just like having an air mattress on a swimming pool, and you sit on the air mattress, it sinks into the pool. That weight of the ice causes the lithosphere to sink into the cenosphere, and the cenosphere is the part that is basically is more ductile, than it's not solid. Now, but this gets us, so that's if we remove the ice instantaneously. If we allow the continents to rebound after the ice gets removed, we see that the East Antarctic portion over here basically rebounds nicely. West Antarctica stays below sea level, and that's a whole nother story. It's partly because of subsidence as well as erosion. The other thing I just want to mention is that the Greenland ice sheet, if it all melted, it would rise sea level about 7 meters. If the West Antarctica completely melted, it would rise sea level only about 3 meters, and that's because lots of it is below sea level. The East Antarctic continent is mainly above sea level. And so it would, if all the ice melted in East Antarctica, sea level would rise around 58 meters. Okay, that's a lot. Okay, so you're probably thinking, well, doesn't this haven't we always had ice sheets, right? And no. So this little diagram here, this is age in millions of years, then cutting over to billions of years. The black represents how big the ice sheets got away from the poles. So the dashed line means no ice sheets, or ephemeral, small ephemeral at the most. And so you can see that most of the Earth's history is ice-free. Anybody who's in my historical geology class, and I see a couple students right there, will go, yes, I know that. Okay, and so less than 20% of Earth's history has large ice sheets. So basically, how do we develop long-term climate records going back millions or tens of millions of years? And so one of the ways is, so a little before I start, let's give some definitions because some of the diagrams have this. First of all, eustasy, which is global sea level. And the old definition is the rise or fall of sea level relative to the center of the Earth. And that's not we want to match apples to apples when we're talking about sea level versus ice volume. And this does, you have to basically remove the water loading effect of that. And so I came up with the term apparent sea level, which is just eustasy and removing the water loading effect. Other people have come up with their own terms, eustatic sea level, so on and so forth. Okay, so you'll see ASL, ESL in some of the diagrams. Just be aware that's global sea level. Now, one way to measure ice volume / sea level changes is to look at the stratigraphic record, because we have a continental shelf, sea level goes up. We are going to have different lithofacies or different sediments when sea level goes up, and when sea level goes down, it's going to change, as well as any of the fossils that live in the sediments. However, there's a triad of processes that control the stratigraphic record. One of them is global sea level. Okay, that's right, and that's what we're trying to get. But there's also tectonics, subsidence and uplift of the crust, loading as we put sediments onto the crust, it sinks. We have compaction from the sediments below getting compacted, thermal because passive margins are still cooling. And then there's a whole flexural aspect that you need to to look at. And that's because if you put a load in one place, it's not going to subside right there on a thick continental crust. It's going to, the whole crust will flex. And then we have to talk about sediment supply. Okay, they can fill in a basin. Another way is to look at oxygen isotopes from Forminifers. I'm going to show you a picture of those in a couple of moments. And but however, oxygen isotopes has two variables. It can measure ice volume, which is kind of cool. Little fossils sitting on the bottom of the ocean can tell us something about ice volume. But it also tells us about what the water temperature is when the shell was formed. There's other aspects that we should take a look at, like evaporation and precipitation effects, but those can be modeled out. So it's really two variables. And if you remember from 7th grade algebra, two variables, one equation, that's bad. Okay. However, there's a new proxy, not new, it's 20 years old, magnesium calcium ratio, that is just picks up the temperature, or at least we thought it was only affected by temperature. And so that means we can dial out and the temperature and then just isolate the ice volume signal in oxygen isotopes. Okay, and then also we have direct evidence. I won't have time to talk about direct evidence, getting cores right next to Antarctica or Greenland. However, those are much more complicated because you have the ice sheet, and that really changes the sediment type and it makes it much more complex. So I won't show those today, but you should be aware of that. So estimating global sea level changes from shallow marine stratigraphy. To isolate the eustatic signal in the sediments and the fossils, we have to do backstripping. It's an iterative process, at least 2-dimensional backstripping or 3-dimensional backstripping. And basically what we do is that we have an initial profile here. And then, with computers, we remove that layer. We decompact the sediments that were below it. Okay. Then we flexually unload the sediments. Then we remove the flexural thermal subsidence, and then finally account for water loading. And so you do this, you know, typically you do this with a program. I actually did it with an Excel spreadsheet. It was awful, but that's what I did for my PhD. And the result is that we were able to reconstruct the straddle geometry of the New Jersey passive margin. And so these are the cores that we took. This is New Jersey here, Cape May. Here's the cores. I extrapolated them along strike to make a dip profile. And then putting them onto a dip profile, we have this lithophases here, or the sediments. The O's and the M's just represent sequences which are basically bounded by unconformities, okay? And so O1 is the oldest in the Oligocene, E is for Eocene, and KW is actually for the Miocene, okay? And so, and you can see, you know, this, the straddle geometry, the oldest one thins out, and then the next oldest one is thick here, and then it thins out, so on and so forth. The next thing what I did, is I looked at the Forminifers in the sediments. And Forminifers, benthic Forminifers, they live in the sea bottom, and they are very sensitive to different environmental changes. And most of those environmental changes are constrained by water depth. So they don't have little water depth gauges on the pseudopods. They actually just, it's the different variables, sediment type, oxygen, nutrients, so on and so forth. And so I identified 10 different biophases. The shallowest is A, B, and C. The deepest is going down to J in here, okay? And we put it, and this is actually showing the decompacted sediments now. And based on this, we're able to reconstruct the straddle geometry of the New Jersey margin here for the time period from 23 to 34 million years ago. So this is just a series of time horizons here of the reconstructed, and you can see basically this is a prograding wedge out here. This was actually the shelf break back 27 million years ago, okay? So the shelf break today is almost 150 kilometers offshore of New York City. But back in the Oligocene, 27 million years ago, it was way back right next to the shoreline of New Jersey, to the present day shoreline of New Jersey, okay? So once we have this, now we can put the benthic foraminiferal biophases on there, and we can get water depths. Some of them we were able to get from previous studies, but what we did is that we put time horizons, and then these are the different sites in here, okay? And then we can put the biophases, and what was so successful about this project is that we had an internal consistency. So on each time horizon, very often we have 1, 2, 3, sometimes even 4 sites along the time horizon, and we would look at the biophases, water depth estimates, and they would all make sense. They would all be consistent. And for some of the deeper water biophases, we're able to calibrate and get water depths. Just so you know, as you get deeper, the error bars get bigger. So in shallow waters, plus or minus 10 meters, in deeper waters, plus or minus 30 meters. And so, and I won't go through this, but you can imagine after we've done all the tectonics, we decompacted the sediments. Now the only thing we have to do is just put one time horizon after another with the biophases water depths and see what happens to the water depths. And these water depths now are actually eustatic changes because we've taken into account compaction, subsidence, so on and so forth. And from that, we were able to construct a global sea level chart. This is just from 28 to 24 million years ago. The dark blue line represents the best estimate. The light blue area is the uncertainty. And for all the students out there, especially the graduate students, and don't be afraid of your uncertainties and show off your errors, okay? Because otherwise, I just had this line in here, you know, I'm basically not telling the truth. Okay, you gotta show off your uncertainties. So that's how you would do it with stratigraphic with stratigraphy from continental margins. Let's switch over to the next proxy, which is stable isotopes. And there's two isotopes that we use, oxygen-16 and oxygen-18. 18's got two extra neutrons. That makes it a little heavier, which makes it a little bit more susceptible, doesn't evaporate as much, and it rains out quicker. And the result is that if we have some evaporation taking place near the equator, as it evaporates, the 18 stay behind, and oxygen-16s are preferentially evaporated. As that vapor moves away from the equator, more of the oxygen-18s rain out and then eventually snow out, and that enriches, the water vapor gets enriched in oxygen-16. So by the time you get up to high latitudes and you got glaciers, the oxygen isotope values are super depleted in 18s and super enriched in 16s, and these negative values represent super depleted oxygen 18s or enriched oxygen 16s. And so the result is that if we can get some shells that have calcium carbonate, CaCO3, we can look at the oxygen isotopes and try to figure out ice volume, okay? However, there's a problem, because when the oxygen isotopes are incorporated into the calcite, there's a fractionation process. So this is just showing the relationship between temperature and oxygen isotopes. It's almost linear. It's almost linear. Okay, and this is the equation right here. Okay, so we have two variables, one equation. We have a little bit of a problem. And so how do we understand? This is just a little cartoon, okay? But I just wanted to show on how we understand past climate changes. This is from a friend of mine, Howie Shear. And we basically look at microfossils. We can look at nanofossils, which are autotrophs, and same thing with diatoms. They're photosynthetic. This is a cartoon. Forminifers do not look like this. This is such a cute cartoon. We have planktonic ones, epifaunal benthics, infaunal benthics, okay? And we can basically look at the chemistry of the shells. We can also look at the mineralogy of the sediments. We can do the chemistry of the sediments. And from all those, we can back out paleoclimate changes. And so let's take a look at some pictures of forminifers. This is about 1/3 of a millimeter across. Okay, so you can fit 3 of these within a millimeter. That's how small, so you need microscopes. And these are pictures of this species here, the Cibicidoides, and here's the Eurodrina. We don't use these too often, but they're so pretty, I decided to put it in. But this is what my students are looking at. I have 3 undergraduate students working on picking Cibicidoides right now, in fact. And so forminifers are fantastic, because looking at the geochemistry, they have become the Swiss Army knife of paleoceanography. They can figure out past climate changes, ice volume changes. I already told you with magnesium calcium, we can figure out paleo temperatures. We can figure out deep water circulation, paleo productivity, and even ocean's acidity. Why is ocean acidity important? Well, to surface waters, when the oceans are in equilibrium with the atmosphere, with CO2, ocean acidity becomes a proxy for atmospheric CO2 conditions. And that's how we get our CO2 records from little forminifers from the bottom of the ocean that lived on this in the planktonic, in the surface, but now were deposited and buried on the sea floor. So this is some of the tools that we use, and we use very often forminifers. Okay, so this is an oxygen isotope chart here, graph here. Y-axis is millions of years ago. You don't have to know about these numbers here. What I want you to know is that higher values represent colder bottom water and or more ice, so it's colder climates. And lower values represent warmer bottom water temperatures and or less ice, so warmer climates. And as you can see, today's 0, the last couple of million years has been the coldest we've ever seen. We've seen in the last 66 million years. In fact, you could go further back. And the last time we've had ice sheets as large as what we've had in the last couple of million years was probably about 280 million years. So for my geology, historical geology people, that's late Pennsylvanian to early Permian. Okay, so what does this graph show? Except that, you know, we go back in time, it was a lot warmer, then there was a big chilling right here, and then a more gradual, another cooling in here. What does this all mean? Well, you can figure out at 2.1 per mil, anything to the left of that, anything greater than that, you have to have some ice. You must have some ice. And any values that are greater than 3 per mil, anything to the left of this, means a fully glaciated Antarctic ice sheet. A fully glaciated Antarctic ice sheet. And so, and then 3.3 per mil would include West Antarctica, it would include Greenland, and also a climate as cold as what we have today. I know it's warm, and so you go, Dr. Pekar, why is it cold? Remember, in the past, we've had much warmer climates. Okay, so one of the things that I did from my sea level records is that I had sea level records, and these are sea level events, or ice volume events, actually, to be more precise, and I compare them to oxygen isotope amplitudes. And this is from different sites in here. Here's the calibration, here's the R square, pretty good correlation. And so I was able to basically develop a means of assuming that the temperature would change at the same rate from each site from glacial to interglacial times. Okay, and so this was, I was able to show this. However, the magnesium calcium records have been being used for the last 20 years now, where they can basically, they're used for the water temperature during calcification. And so we can isolate the isotopic value of seawater and therefore constrain ice volume. However, with every golden proxy that comes out, is, you know, it first comes out, oh, this is great. Golden proxy. But then problems started arising. Deep burial changes, diagenetic property changes to magnesium calcium ratios, dissolution. Temporal seawater changes through time have been modeled. So there is uncertainty, but I think there's a good consensus with that. However, this one, the saturation state effect on benthic Forminifers, has been the one that has been the worst. And so let me show you, in 2000, you know, we're talking about 17 years ago, I was developing a record here showing oxygen isotopes here, bottom water temperatures based on the magnesium calcium, and then I was backing out ice volume here, the oxygen isotope value of seawater, okay? This is millions of years ago, 16 to 18 million years ago, and this site was from off the coast of Tasmania. And I look at this and I go, well, wait, there's something really weird here going on. So basically, when you start looking, and I'll just go to the punchline here, that when we had higher ice volume, bottom water got higher. When we had less ice volume, bottom water temperatures got cooler. Ouch. So I said, oh, okay, wait, this could be a great paper. This could be where we have, you know, deep water changes, warmer deep waters during glacial intervals. That could be cool, but the very next year, or it was ion saturation. We didn't know about this at the time. So the very next year, this paper comes out from Kerry Lear, from the Central Pacific, from the site 1218. And so this is oxygen isotopes, this is magnesium calcium, or this is the oxygen isotope of seawater based on, and this is water temperature, and guess what? She sees the same thing, this anti-correlation between oxygen isotope values of seawater, which is ice volume, and water temperature. So there's a problem. And so basically, I'll cut to the quick, I cut out the slides on the history of this, but the cut to the quick, basically, after different attempts at different ideas, and Kerry Lear is one of the best geochemists around. She worked with Yair Rosenthal from Rutgers, and they came up with saying, look, if it's because of this, there's not enough carbon on ions, it's not saturated enough, maybe instead of taking epifaunal forams that live on the sea bottom, we take them from just infaunal, just shallow infaunal. And that's an older carbonate from the oldest shells should buffer and keep the carbon ion saturation pretty high. So they started using as shallow infaunal autosolus, and guess what? It seems to be working the best. Okay, and actually my students are also picking autosolus as well. So we can try to back this out. So I just wanted to show you this. So let me show you for this part of the talk, I'm going to talk about different time slices and then compare ice volume and carbon dioxide. So this actually just came out just about a couple months ago from my former advisor, Ken Miller, in Science. And so this is millions of years ago. On the left side, oxygen isotopes from certain sites that he thought were good, magnesium calcium records showing bottom water temperature, sea level, using oxygen isotopes and magnesium calcium, and then the smooth sea level from his backstripped stratigraphy, as well as magnesium calcium estimates. And then here's the CO2 records in here. This is an amazing summary paper, and he's been working on this, I guess, on his entire career. And so the time periods I'm going to look at today is the late Miocene, when CO2 was similar to today, to as low as pre-industrial. I'll talk about times in the Middle Miocene, about 15 million years ago, when CO2 was higher than today, up to 550 parts per million, and today's CO2 levels are around 415. We'll look at the later Oligocene, which was basically, there was a debate about the later Oligocene. I'll talk about the big change that happens, the climatic change. You can see in the sea level where sea level's low and then that is high in this part and then drops right across the 34 million years ago. And then I'll just quickly end with the Middle Eocene between 42 and 50 million years ago, when carbon dioxide was well over 700 parts per million. So let's look at the late Miocene. So as a matter of fact, let's first look at this whole record here. Here's Asian here, here's oxygen isotopes. So going down is colder. And you can see the Middle Miocene, much warmer, gets colder here. In the Middle Miocene, it's kind of boring. And in fact, the MI5, which is considered to be an ice volume increase event, we barely see it in her record. And this is the best record we have. I have a graduate student who's coming up with a record not quite as high as this, but it'll be a second high resolution record for this time period. And so you can see that's, not much is happening, but there's supposed to be a big ice volume event in here. So I had a former graduate student, and we were looking for the late Miocene. And we had a site that I was part of drilling over in East Antarctica. Had fulminifol chalk, so there was forams. However, the forams were diagenetically altered. So the oxygen isotopes were foobar. So I looked around the coastline and found another site that had carbonate in it during the late Miocene, because for almost the entire time, from 22 million years all the way to my almost recent, the waters of Antarctica are so corrosive that you don't get carbonate preserved in the deep water. And so we found another site, 689, that had carbonate preserved as well. And he ran the forams for oxygen isotopes, and guess what? We have an oxygen isotope record. But we expected a warming to take place because there was some evidence that a late Miocene warming was taking place. The values come back, and we get values that are over 4 per mil. And remember, I said 3.3 per mil is consistent with cold bottom waters and a fully glaciated, like present day Antarctic ice sheet. And we're getting 4. So that means that it was cold, just not cold waters, this is waters at least as cold as today near Antarctica. And so this site here was just 600 kilometers off the coast of Antarctica. And he develops this record in here. I won't talk really about this, the carbon isotope values, because we're talking about ice volume in this case. And so we couldn't get magnesium calcium to work. We only got 2 values. But the first takeaway is that the very high oxygen isotope values was greater than the modern global ice volume. Okay, so we said, okay, so we don't have magnesium, calcium, and we only had two values that worked. Let's take a look at what the present day water temperatures are at this site, which is Maud Rise. And they get as cold as about -1°C. So we started with the coldest possible water, -1 to 0 to even +1, but +1 was too warm because it would give us an ice volume that was too large. But even with the coldest values, we get up to about 50% more ice than today, which means that it had to come from the northern hemisphere, because by this time the Antarctic ice sheet was quite stable and the land area has already shrunk to near present day size. So this had to be coming from the northern hemisphere. And the takeaway is that significant northern hemisphere glaciation may have occurred about 8 million years older than we previously thought. We thought that first northern hemisphere ice sheets greater than Greenland, okay, greater than Greenland, occurred about 3 million years ago. Here we're saying about 11.5 million years ago, 11.6 million years ago. So this is occurring just when CO2 is near present day. And this makes sense, actually, okay, so that we can have a larger ice sheet perhaps in the northern hemisphere if CO2 gets near present day or a little bit lower. Now let's take a look at the Middle Miocene. That's between about 14 to 17 million years ago. This is the same one where we see very high, very low oxygen isotope values that are consistent with a great deal of warming. So again, Ken Miller came up with a paper just recently, and he suggests that during this warm period, 15 to 17 million years ago, sea level dropped, and part of the ice sheet dropped to about 20. He said that maybe it could have completely collapsed, but it's around between about 30%, about 50% of what we have today, to maybe a complete glacial meltdown during this time period. And this is when we had CO2 values of around 550 parts per million. So we're talking about sea level falls of up to 50 meters and then 50-meter rises. The big controlling factor for this is actually those changes that I was saying about the shape of Earth's orbit and its axis, but even longer time periods, a 1.2 million year cycle that we see, that's the dominant sea level cycle, okay? But that you don't have to know about, okay? So this is some records that I put together. This is basically calibrating oxygen isotopes sea level. So here's oxygen isotopes. This is the calibrated oxygen sea level estimates from two sites in here. And again, when we get into the warm period in here between 16 and 17 million years ago, I see the ice volume decreasing by half to maybe 75% of the ice sheet. That would result in the ice sheet retreating onto the plateaus of Antarctica. So, and then for the rest of the Miocene, the early part of the Miocene in here, we have CO2 levels that are around today, around 400 to maybe as low as pre-industrial. Okay, and you can see that right in here. Okay, and the ice sheet was actually, sometimes it got a little larger than today, but most of the time the magnitudes were near present day levels, and then it would retreat to maybe about half of the ice volume. Okay, and this is CO2 levels between about 250 to about 450 parts per million. So that's the Middle Miocene, okay, and this is some of the events that could have been representing when ice volume was actually higher than today, Okay, so let's go into the Oligocene. And this is actually where I did my original PhD, so it's kind of like coming home in certain ways. During this time, CO2 ranged from about 300 to 800 parts per million. And when I was giving this talk to NASA, some of the scientists told me that some of the CO2 values for the Oligocene are being reevaluated because it's a new proxy and things like that. So, but I just wanted to mention that some of these values that are up to 800 parts per million may be a little bit too high. Some takeaways is that sea level range from about 40 meters, about 40 meters below what we have today, so it was warmer, to about 30 meters above. Okay, so sometimes the sea levels, the ice sheet got bigger than today, and sometimes it retreated to about half of what it is today. So how do we get an ice sheet bigger than today? And I'm not saying that there was northern hemisphere ice volume at all. Okay, so how do we do that? Well, this is what Antarctica would look like if the topography, after we remove the ice and isostatically rebound the lithosphere. Okay, and you could see big embayments in here, large embayment into Ross Sea, Weddell Sea, lots of West Antarctica underwater. However, it wasn't always like this. So during the Oligocene, there was some studies done from Wilson et al. 2012 and then finally 2013. And what they did is that they said, look, there was a great deal of erosion due to the glaciation, as well as a great deal of subsidence in Antarctica, especially in the Weddell Sea, as well as in the Ross Sea. And so they reconstructed based on a minimum reconstruction topography, and you could see that the West Antarctic subcontinent just pops up. It's all above sea level. And the Ross Sea suddenly has these long, elongated islands in here, and the maximum reconstruction almost destroys most of the Ross Sea, in fact. And we have land extending way out into the Ross Sea in here. And so that results in 25% more land area than the modern. And since the ice sheet would bows out, we can have 1.4 times more ice volume than today, equivalent to about 85 meters of sea level change. And so this is right from from the paper. This is today's topography. This is the minimum topography, resulting in about, if all the ice melted on a fully glaciated Antarctic ice sheet, resulted in about 83 meters of sea level change. If all the ice melted with the maximum, it grows to about 89.5. So not too much of a difference. And so what was controlling the ice sheets back then? Well, one of the things is that we have these 1.2 million year events. Okay, and then, like I said, these 1.2 million year events have been shown for the Oligocene, whether it's me or others, that they seem to coincide with sea level falls. These are oxygen isotope values, events that infer ice sheet increase. And you can see there's a pretty good correlation with most of them, but not all of them, okay? And that's because there's a water temperature that could maybe mask part of the ice volume signal. And so this is from a paper I did a while back, but it basically showed this one-to-one correspondence. These are basically sequence boundaries that are sea level lowering, and they coincide with the 1.2 K events all the way through, okay? So the control for most of the big ice sheet advances in the Oligocene and most of the Miocene have been shown to be due to these changes in Earth's orbit shape, as well as its axis. So here comes a conundrum. Okay, in the late Oligocene, between 23 and about 28 million years ago, we see a big decrease in carbon dioxide values. Okay, that's considered to be realistic. We also see in the oxygen isotopes, and this is a composite of all the records here, we see the oxygen isotope values decreasing, which suggests warming. So we have decreasing CO2, should be cooling, but we have warming based on oxygen isotopes. And a paper in 2005 that was in Science said, for the late Oligocene, there appears to be a decoupling between CO2 and the climate records. And all thing I could say is, thank goodness Rush Limbaugh does not read Science, because that would have been, you know, it would have been on his radio show. So there's a problem here. Okay, so how do we work this out? How do we work this out? Okay, well, this site here, site 690, you can see how much higher the values on. This is right next to Antarctica. So this is below the Antarctic circumpolar current. So it's not going to be, it's not going to have any warm water currents abutting it. And it suggests that these values super high while everything else is getting lower, that this could be a better record because maybe bottom waters were warming up during this time. Who knows? Let's find out. Well, a former PhD student of mine who's now a professor at the University of Houston, he did one of his chapters. This is just one of his chapters. He got samples from site 690, which is right up against Antarctica. Here's the Antarctic continent here. Here's this box here. Here's 690. This is the most southerly site in deep water that has the preservation of carbonates. Wow. So he starts doing the oxygen isotopes, and guess what? Here's the blue line here. It just diverges away from the other records. It diverges away from the other records. And this suggests that these records here are being, because they're both being controlled by ice volume, the same ice volume. So this is going to be some sort of warming of bottom waters in most of the ocean basins. But right next to Antarctica, the water temperatures stay cold. And so remember, anything above 3 per mil is consistent with a fully glaciated East Antarctic ice sheet. So we have, instead of, they were saying a collapse of the East Antarctic ice sheet during this time, and he's showing, or we are showing, that the Antarctic ice sheet was, would sometimes collapse a little bit, but it was actually at full growth during glacial maxima. And so the big takeaway, it suggests that a warmer deep water mass bathed most of the ocean basins. The ice volume did not decrease as suggested by other records. Thank goodness, otherwise Rush Limbaugh would have been right. We don't want him to be right. Okay, so that's the later Oligocene. Now, the Eocene Oligocene boundary is the most profound, permanent climate transition of the entire Cenozoic, the last 65 million years. This is the most largest and permanent climate transition. Oxygen isotope values increase, so it's getting colder, and we see sea level estimates anything from 55 to 85 meters of sea level fall. So the ice sheet went from near zero to larger than today, 30% larger than today. And the CO2 records are not as clear because right across this boundary here, there's problems that were shown to me or mentioned to me when I was giving my talk for NASA. Okay, so and just for some detail, we actually see a small cooling here, another cooling, and then the big cooling finally up in here. And so this takes place, it takes about 100,000 years to go from basically almost no ice to a fully glaciated Antarctic ice sheet, probably larger than today. And so what I would like to share with you is something I did a couple of years ago, and it's a summary of what we think the state of ice volume is for the Oligocene from 23 to 34 million years ago. And so the ice volume during the glacial minima was about as small as maybe 25 to 50% of present day, but during the glacial maxima, it got larger than today. And so these are different studies that were done. And you can see that here's Hopvogel's, the latest one in here. And MI is just for the very top, very end of the Oligocene. This is the base of the Oligocene. This is the middle of the Oligocene. OI2b is at 26.7 million years ago. And you can see that there's a nice consensus where, I had to go back and look at what their uncertainties were, and if they didn't show uncertainties, for me to estimate it. And you can see this rose-colored box here. It shows that the ice volume got maybe around as small as maybe 20%, perhaps, and to maybe up to about maybe 40% of the modern ice volume of today. The maxima, on the other hand, okay, we're talking about at least 100% to maybe 140% of, or 40% larger than today. Okay, so this is actually ice volume and sea level. Sorry, so from 25% to maybe about 70%. Okay, and so we have a nice consensus now. Okay, we're never going to get exactly how big the ice sheet was at any one time because there's always uncertainty in our proxies. And so the last thing I want to just mention is the Eocene. Okay, and that one occurs from 42 to about 50 million years ago. And in this case, I was looking at sediments on a passive margin south of Australia. And what we see, the little red is sequence boundaries or sea level lowering. The stars represent sea level falls from another record from near Australia. This is from the New Jersey coastal plain. This is from Alabama. And we see a pretty good correlation between the sequence boundaries from different locations. Whoops, it's really kind of gone crazy. There it goes. From different margins. And when you see sequence boundaries occurring at different margins, at the same time, that suggests a global mechanism for sea level falls. And the only one for that is basically ice volume. And so how big was the ice volume when CO2 was so much higher than today, from 700 to maybe 9 or 1,000 parts per million? So this is the ice volume events, and here. And what I did is I looked at the oxygen isotope increase, the maximum values, and then I won't go into detail how I did this. I calculated the low end of sea level change as well as the high end, took the mean. Then you had to include basically contraction as sea level as the temperatures cooled of the oceans to get a final sea level change. And what we see is that the sea level during these warm periods were, first of all, the ice sheets were ephemeral. They were ephemeral. That means short-lived, only during special times when the Earth's shape of its orbit and its axis was in a favorable condition for ice to form at the poles. And we can see that the ice volume here is about a third to maybe half of what we had today. And this is what the ice sheet would look like at about, if equivalent to about 25 meters of sea level change in the lower left-hand corner here. And you could see that, and this is from the old study from Rob DeCanto from 2003. DeCanto and Wilson did the new topography that shows a lot more land. And I've always asked Rob to please redo this for the new topography, but he didn't. He's working on IPCC and other things. But you can still see that the ice sheet never reaches the coastline. And even when it reaches 40 meters or 2/3, it still doesn't reach the coastline. It does not reach the coastline. So, and that's why we may not see much evidence of an ice sheet around Antarctica during this time period. And so that's my, I just taken you through a whirlwind of different time slices. Let's talk about the elephants in the room of how paleoclimate can really allow us to look into our future, okay? And so there's two elephants in the room. First of all, tectonics and landmass and oceanographic changes have occurred through time, okay? The other one is timescales, okay? Today's timescales, we're talking about decadal to century. And we have a thermal inertia where the climate system, even after we put in CO2 in the atmosphere, it's going to take time for the atmosphere to warm, then the waters to warm, the oceans to warm, and then finally the ice to warm. That's thermal inertia. And so, and the paleoclimate records, for me, high resolution has resolution in the thousands of years, okay? Thousands of years. So let's talk about some of the tectonic differences. We have changes in the Mediterranean, okay? That was basically seaway between the Indian and Atlantic Oceans. We have the Panama Seaway that was open, that was a seaway until about 3 million years ago. Indonesian Seaway is closing right now. It started getting restricted around 8 million years ago. On the other side of the coin, we have opening of seaways. So we have the Tasman Seaway was closed until about 51 million years ago. I'm actually working on a project with some scientists in that right now to talk about that again. The Drake Passage used to be closed. We're not sure when it opened. It's a lot of uncertainty, anything from 40 million years to maybe 25 million years ago. And with the opening, with those two new seaways, we end up with Antarctic circumcurrent. And that finally formed in the later Oligocene, okay, in the later Oligocene. So other things, other tectonic differences. We have the rising up of mountains, the Tibetan Plateau starting, anything from 40 million years ago to today, still rising. We have the Andes Altiplano, okay? There was mountains along there for the last 100 million years, but the Altiplano rose up only in the last 5 to 10 million years ago. Same thing with the Colorado Plateau. It's relatively new. So all these changes will change the jet stream and the weather patterns around the world. So what I look at is on the million-year timescales. The ice cores look at thousands of years ago to hundreds of thousands of years ago. We are just looking at the next couple centuries. Okay, 2200 is when Captain Kirk was going to be born. Okay, so we're talking about very short timescales compared to what I look at. And then the other aspect is thermal inertia. Thermal inertia is your friend until it isn't. So right now there's a climate inertia, okay? And we have climate change pulling this climate inertia is like on like a spring here. And the result is that at some point there's going to be an increase, a dramatic increase in climate changes. And this is what one author, James Hansen, the NASA scientist who spoke to the Congress 30 years ago about climate change, one of the leading climate scientists of our generation. And he came out with a paper that said, no, sea level's not going to rise 3 feet in this century. It could rise 3 meters. And that's because of climate inertia. At some point, the ice sheets are going to start melting much faster than they are today. And so inertia, so the last thing is thermal expansion. The oceans are going to continue for centuries. Ice sheets are going to continue for centuries to the millennia. Okay, that's what thermal inertia is all about. And this is just a little cartoon from old IPCC that I don't think they ever really updated it, but it showed, once we stabilize CO2, it's going to stay in the atmosphere for hundreds of years, even after we decrease CO2 emissions. And sea level is just going to continue rising for centuries to the millennia. Okay, so that's, and my records are always, well, most of the time, where the climate is in equilibrium with the forcing mechanisms, like changes of Earth's orbit shape and stuff like that. So the takeaway, while past climate records may not be useful for immediate future climate changes, like the decadal timescales, the long-term, centuries to millennia, can be a good, give us a good idea of what our future could be like. Okay, and so in summary, the late Miocene, we had episodic northern hemisphere glaciation. Middle Miocene, with higher sea level, CO2 levels, the ice sheet collapsed to maybe a quarter or a third of what the present day. In the Oligocene, because the continent was much larger, Antarctica had a much bigger ice sheet during glacial maximum, but still retreated to about 30 to 50% of the modern. And in the Eocene, when CO2 was much higher than today, the ice sheet was ephemeral and probably didn't exist. And then temporal differences. Today we're talking about decadal changes. My records are hundreds of thousands of years. And so tectonically, we're looking at basically, there's been changes through time, and that will affect climate. So in some paleoclimate records can provide key insights to what our planet was like under elevated CO2 conditions, and it can provide insights for future changes, especially at the longer term. And with that, I want to thank you for listening, and I'll take questions.
Thank you so much, Dr. Pekar. As you can see, the chat window is full of questions. So I would,
fantastic.
I think we can probably just scroll up and start at the top. I think we've got a lot of students that are in attendance today.
So, so Dax, can you do me a favor? Could you do a screen grab of the participants, because some of my students are going to be getting extra credit for this.
Yes, okay. Absolutely.
Okay, thank you so much. Okay, so let's go through some of the questions. Let's see, where's the first question though? Okay, are there any subterranean processes that could be influencing the temperature of ocean waters that could be contributing to ice loss? In terms of subterranean, not subterranean, but in the ocean, the ice loss is going to be mainly controlled not by air temperature, but by warmer ocean temperatures that are going to be melting the ice sheet. Because like in West Antarctica, the ice sheet is lots of it is below sea level. So the ocean water is a liquid. It's not a gas like the air, so it has a higher heat capacity. It can melt the ice faster, and so a slight warming at ocean temperatures will have a much more disastrous effect on the melting of the ice. And then is CO2 concentrations across the latitudes and longitudes of the planet, and how important are local disturbances? Well, at the long-term records, we can see events down to a couple tens of thousands of years, thousands of years. Okay, in terms of local disturbances, we just can't see them, or they may be seen in one record, but then not another record. And that's one of the important things. We can't have just one record from any one time slice. Okay. So, do ice caps act as a sort of reflective shield? Absolutely. Okay, and so the ice caps are white. They reflect the sunlight back into space and keep it cold. So as you shrink the ice sheet, you're going to have more terrestrial land area exposed, and that's going to absorb the heat. What about meteor activity also impacting the carbon? Okay, there are there's evidence of asteroid impacts. We know about when the dinosaurs got wiped out, but we do know about smaller ones like the Chesapeake Bay area that hit around 35 million years ago, but it didn't seem to affect the climate at all. Great question too. Okay, not knowing what you study, Dr. Pekar, I would like to know your opinion on thermal expansion. Yeah, I only mentioned it briefly, and I should have had a slide on this, I guess. What causes sea level changes? Thermal expansion is instantaneous. When you warm the ocean, it expands immediately. So most of the sea level rise today is actually due to thermal expansion, not ice volume, but the melting of the ice is catching up, okay? And how big of a factor you play in climate change? Well, even for that old period from 42 million years ago to 50, I had to include that expansion and contraction of seawater in my equations to try to back out global sea level changes. Okay. Hi, Professor Pekar. I want to know more about what interested you to study geology. Because it's the study of Mother Earth. It's basically, the Earth is where we live, where it has an incredible history, the evolution of life itself, and when you study geology, and my first thing was fossils, and then geology, and then climate. And geology brings them all together. Okay, so whatever you like, exactly when I talk to students, introductory students, I tell them, I go, any aspect, any science that you like, there's a profession in geology for you. Okay, if you like physics, we got geophysics, like chemistry, like geochemistry, you name it. So, okay, so that was a great question, thank you. For Michael, as parts of the Earth still adjusting to isostatic equilibrium from the former glacial coverage, yeah, actually it is, okay? So the last ice sheet started melting around 17,000 years ago, had to switch gears. And 17,000 years ago, we had an ice sheet 3 kilometers thick over North America. In Canada, it's still isostatically rebounding, okay? So it's still happening today. I actually asked somebody who does this for a living, who models this, and I said, so how much of the rebound has taken place? And he said about 2/3 to 3/4. Okay, so we've done 17,000 years, and we're still about 1/3 of the way, still yet to go. Okay, Alex, stop global warming. Stop global warming is the cause of the sea level rise. Yeah, but if we can stop global warming, it'll cause the ice sheets to stop melting. It'll cause the expansion of seawater due to the warming to slow as well. How is the impact of ice volume changes on our environment, and how can human society respond properly to them? The impact of, well, you know, we're going to be in trouble. The impact of ice volume changes and decreasing is going to cause sea level to rise. That's going to, you know, our cities, many of our cities are on the coastline. Lots of our property is on the coastline. And we're going to have to either try to slow climate change, or we're going to have to abandon parts of the coastline in the future. Okay, that's a whole nother talk. Okay, so what's the importance of warming of the sun and our climate and glaciation? So and this is, you know, I could have had slides about this, but the sun intensity is actually decreasing right now as climate is as the climate is warming. So so it can affect us in a minute way, but not the way CO2 or even the changes in Earth's orbit and axis can affect it. Okay, so but on the long term, hundreds of millions and billions of years, the sun was cooler. Okay, a billion years ago, the sun was about 15–20% cooler than today. Okay, but we're talking about the most important word I just said was billion. Okay, what is the most efficient and fastest way to stop global warming? Vote. Okay, that's the most effective way. Right now we have a climate denier who calls climate change a hoax and that windmills cause cancer. There are 5-year-olds that know climate change better than that. Okay, so
4-year-olds. I've got a 4-year-old.
I'm sorry?
I've got a 4-year-old.
Oh, I'm sorry. Okay, so the 4-year-old knows climate change better. Exactly. They don't want to diss anybody less than 5 years old. Okay, so so you know, we got to vote. Okay, and you got to, I would say, become educated. Our corporate media does not do a good job in explaining what climate change is all about. You have to go to like there's a UK newspaper called the Guardian newspaper. They have climate every day. But also go to organizations that talk about climate change, 350.org, the Yale Climate Communications. They can give you the background. And go listen to talks by Michael Mann, you know, when he's on the TV. He's award-winning scientist who does climate change in the last couple thousand years, okay? That's how we can do this, but vote, okay? We can vote. I already voted in person. The line was 30 minutes long, okay? So I lost track of where we are. What's importance of sunlight? Fastest way to stop global warming? Okay, what do you expect from sea level just rising 3 or 4 feet? And what cities and urban areas will be impacted? All of them, anything that's on the coastal plain. New York City with a 3 to 4 foot increase. I give a talk on climate change to the general public, and 3 feet starts swamping Coney Island, parts of the Rockaways, Bangladesh, you name it, New Orleans, all across the whole Gulf Coast gets affected by this. Okay, so it's bad. And that's what the IPCC is saying, 3–4 feet. Other scientists like James Hansen and others are saying, no, it's not 3 feet, it's 3 meters, which is 10 feet, by the way. Global warming, higher temperatures will melt ice and will affect sea level? Absolutely, okay? And, okay, I have a question for you. I have a question about the expedition. How much is it to go with them? Okay, they pay me. Okay, so if I go on an expedition, it's 26 countries all working together, and they all contribute money. The United States contributes 1/3, so we get 1/3 of the scientists, and they will pay Queen's College. So if I leave on an expedition in the middle of the semester, they will pay Queen's College to let me go. Okay, and Queen's College has always been great. You know, I've seen universities, they go, no, you got to continue teaching even if we're on the expedition. And Queen's College, they go, you're on an expedition, we will find someone to teach for you. No problems, ever. We've never had a problem with that. then super supportive. Is it possible to stop sea level rise and bring back glaciers? Bring back glaciers? No, I don't think that's, we're talking about hundreds of thousands of years. We can stop sea level rise if we can get our acts together. What Greta from Sweden was saying about the IPCC, we have a carbon budget and it's going to run out in about 8 to 10 years. And after that, sea level rise will be inevitable. So we really need to get the current, and I hate to be political, the current administration of climate deniers out and get some climate, some politicians who actually listen to scientists in, because this is as bad. When I give my general public talks, my analogy is that this is like a world war, and we're in the winter of 1942 after Pearl Harbor was bombed. That's how bad it is right now. And it's for the scientists, we know how bad it is. The corporate media is not telling you how bad it is. Is CO2 the cause of global warming? Yes, as well as other greenhouse gases like methane. In your opinion, what do you think people should do to prevent climate change from getting worse? I said it, vote and become educated. These are all great questions. I'm just trying to go through them because we're running out of bloody time here. So what areas do you believe will be most affected by the sea level rise? I already said it's basically coastal plains, from New York City all the way down to Florida, around the Gulf of Mexico in the United States, and then other places around the world. And so at one point you said that the shelf break migrated eastward more than 100 miles. I thought that the shelf break meant ended the continental crust. No, that's just where we go from the shelf to the slope. So the shelf break is where there's an increase in the gradient of the seafloor, where the shelf, where the continental shelf is basically low gradient, and the slope is anything from 3-4 degrees on passive margins.
Steve, that's Alan's question.
Oh,
but
okay.
Isn't that the edge of the continent? And I don't see why that should move with sea level change.
No. It's actually, it just so happens that today the shelf break is right where the crust thins. Okay, and actually the crust starts thinning right at the shoreline of New Jersey. In fact, that's where we have this change from unstretched crust to stretched continent, and it gets thinner and thinner as we go further out. And it just so happens that the shelf break is actually over, it's extended all the way out there, and at this point, okay? But the shelf break, the paleo shelf break was right at the shoreline of New Jersey 35 million years ago, okay? So the shelf break is just, the changing gradient, and it just happens to be today right where the crust is thinned. So basically oceanic crust, okay? It's really cool, okay? And so we could talk about it more, okay? Let me just finish this up because I'm running out of time. Well, I'm not running out of time, but how can we track sea level? We know for today, they are measuring it, okay? We can do it by satellite. We can do it by tidal gauges. And then from Paul, were there no glaciers back then? I'm not sure how and just to see, yeah, back 40 million years ago, it was basically ice-free conditions when CO2 was higher, it was 700 parts per million. Did you always have an interest in geology? Yes, ever since I was 8 years old, I was collecting fossils. And, but I had other passions. I loved meteorology and climate. I loved oceanography, and this field that I do, paleoceanography, brings them all together. Great question too, okay? Also, will this affect tidal changes? Not tides, but the tidal gauges are showing sea level rising, okay? Does global warming not just affect animals, but how does it affect people on Earth? It's gonna affect us, okay? We cannot move our cities, we cannot move our crop belts, our agricultural belts. Heat waves are gonna get excessive. There's gonna be parts of the Middle East will become unlivable in many places because of the heat. I can just go on and on, okay? It's going to affect us in it's going to be, to tell you the truth, what studies are saying from the economists, this is going to be a civilization stressor. It's going to stress civilization to near the breaking point. That's how bad it is. So it's just not coming from climatologists. It's coming from economists, from everybody. Okay, how much do you think we'll get to know about the Earth in the future? You know, I'm doing my best to try to look at the past and try to tell something about the future. But as I pointed out, there's always error bars and there's always uncertainties. And just to point out how much CO2 was around in the Cretaceous 90 million years ago. Yeah, so exactly. So in the Cretaceous, that's the time of the dinosaurs, 670 to 90 million years ago in New Jersey. We find pollen from palm trees. We find a clay mineral for the Geology 102 students, kaolinite. And kaolinite is only found in it's a tropical clay mineral. Okay, and it's found in New Jersey. You don't find it today in New Jersey. But back in the Cretaceous, CO2 was over 1,000 parts per million in the Cretaceous. Okay, moving forward, what is the best advice to give a positive impact moving forward? Basically, there is hope for climate change. We have the technology in solar panels, wind turbines, it's really another talk, but we have the solutions. And there's people around the world, the United Nations is doing a great job bringing people together to try to save humanity, save civilization. So don't watch corporate media too much because they're not telling you anything what's happening in the world about on how scientists and just lay people are trying to save the world, okay? So, and okay, wow, there's two, okay, I'll see if I can do a few more. Due to climate warming, the CO2 will reduce oxygen? No, but the burning will, okay? And then, okay, oh, I just got mixed up here, okay? I think I skipped a few. Okay, so I think I skipped a few, so I'm just gonna go over here. So, yeah, I could definitely, okay, so Kwan, how does absolutely no ice affect the ecosystem back there? It affects it greatly. The gradient in temperature from the equator to the poles was much lower. The CO2 was much higher, so it kept the poles very warm. Okay, we're talking about 15 to 30 degrees warmer at the poles. How do you feel if we don't stop global warming now? How does that going to affect us through the future? It's going to be bad. It's going to be civilization stressing or ending. How helpful do you think the new Green Deal was? It was a great starting point. Great starting point. And they've fleshed it out a lot more. And there's a lot of people, every type of scientist is out there working on this. Okay, so and I can give another talk just about climate change. Okay, so why should China's growth rate be reduced? No, in terms of, first of all, China's making everything for the world, okay? So their CO2 emissions, part of it is for us. And then on top of that, per capita, China's CO2 rates are much lower than the United States and probably parts of Europe, okay? So, and that's including all the things they make for us, okay? And it may be the master polluter, but it's making all our toys and all our iPhones and everything else. And then finally, we're down to the last one, Janice. If sea level is going to rise, why do big hedge funds like BlackRock buy mass oceanside properties? Because they probably watch Fox News. I don't know. So I have no clue. Florida is going to be in a lot of trouble, okay, in the future. In other words, the Paris Climate Agreement was not good for the climate because it allowed China and India to keep their emissions high. No. India, first of all, has a per capita CO2 emissions of small fraction of the United States. I can't remember exactly, 1/5 or 1/6 of the United States. China is still, like, even though they make all our toys and all our everything else, they still have lower per capita CO2 emissions. So, and they're still developing. And on the other end, and like not to keep helping talking about China, but China leads in building solar plants, building wind turbines around the world. Okay, we used to be the leaders, but because of the lack of leadership in the United States, China now builds more solar panels than we do. Whew. So I just went through, I don't know how many questions.
A lot.
Yeah, and so so we still have 50 people here. I want to thank everyone. And so for my students, I only did a screen grab in the very beginning. So if you did attend, just email me as well, okay? So I want to thank everyone for coming today. Okay, it was a nice turnout today. And so,
Thank you, Dr. Pekar.
Yes, thank you, Dax. Okay, and we'll talk soon. Okay.
Absolutely.
Okay. Oh, Dax. Yep.
Let's reconvene on. I'll send you a little link.
Okay, sure. Did you did you record this?
Yep.
Oh, you did. Thank God. Thank God. Okay, because my students, some of them couldn't make it today.
Yep.
So excellent. Thank you. And so let's we can. I got to do a few things right now, but we can always Zoom a little later on today.
I'm going to be in meetings for starting in about, looks like 30 more minutes. I'll be starting meetings, so that'll time me up for the afternoon. But it would be great to chat for just a moment.
Let's do it anytime until 10 p.m. tonight.
Okay, I'll let you know when I'm done.
We'll make it easy. Okay. So so how many people showed up? I saw at 1.70, 71.
You're at 72.
Okay. Okay, great. Okay. Hopefully, actually, a professor who I know, I really haven't hung out with him much.
George?
I'm sorry?
George?
No, not George. Actually, he was invited by Alex, the professor from New Paltz, and so I saw a few students who I didn't recognize the names at all. So that was kind of cute. So
a lot of these are my kids.
Excellent, fantastic.
They're all. In fact, they were evaluating you as a potential instructor for next term.
Okay. This is the evaluation. I did have to race a little bit. It was a little bit too long of a talk, but
I think you did great.
Oh, thanks.
Now we got to talk about making sure there are enough seats for them.
Yeah, well, we're gonna have to talk about that. We're gonna have to try to figure something out. You know, like the thing is that if we can get a TA, you know, who could teach the labs, like an earth science teacher, then that takes 3 contact hours away from me, and then we can actually have multiple sections of lab.
Well, let's chat because I think we have the ability. I think that there's a pretty decent chance that we're going to have a demand for your upcoming course.
Okay.
That we'll talk about it.
Yeah, well, let's talk about it later because you know it's kind of a writing intensive, so I don't have to think about it. But let's talk about it whenever you get off. Just email me. I'm going to be busy for the next 3 hours anyway. Okay. And we'll talk about it later.
Okay.
Okay. Thanks again for recording it and helping out and stuff like that. So that's really great. I'm glad that a lot of you students showed up because I wasn't recognizing the first couple students. I'm like, who are these guys? This is great.
No, these are my sections.
Fantastic. Okay. And then, you know, to tell you the truth, Dax, for students, you know, like in 101 or 100, you know, if we have environmental scientists from our department giving a cool talk, from the 100 inside 100, they should be invited to see what the professor's doing. Absolutely. So everything's worked out. I'll let you go. I gotta get going myself. Thanks again, and we'll talk sometime this evening.
Later.
Okay, take care, man. Bye-bye.